Hello, y'all. Welcome to lesson 56 in my DP chemistry curriculum. Today we're going over structure 2.2.3 or 2.3.2. Geez, the strength of metallic bonds and how it's dependent on charge of ions and radius of the metal ion. So we're going to explain the trends and melting points of the S&P block metals using this, and we'll talk about terms of charge of cations and electron density. So we'll make sure we know what we mean by that. So when we talk about metallic bonds, once again, the big thing about metallic bonds is it's specifically dealing with the lattice of the metal and the negative delocalized electrons that float around in between. And we have these attractive forces between them that just spiderweb throughout the whole metal. And this is our metallic bond. So once again, it's between the positive cation lattice and delocalized valence electrons. So that's what our metallic bond is. And when we talked about things like ionic or covalent bonds, we learned that the strength of ionic bond is based on radius and charge. And it's the same thing for metallic bonds because once again, this is all just electrostatic interactions. So these are the forces between charged particles over a distance. So it's always going to be based on charge and distance. In this case, distance is going to be atomic radius. And actually, instead of atomic, it is ionic because these are all cations. And charge is the charge of the cation. And this all comes together to form what we talk about with electron density in two ways. So we'll talk about both ways these affect the electron density. So let's first start off with charge of the cation. Actually, let's start off with radius because honestly, it's more important. So radius is the first one. A small radius equals a greater charge or a greater electrostatic force, which means it's a stronger metallic bond. You can always think about it if you take two magnets and you put them together, having it closer together is always better than having it further apart. And we're always going to have a stronger distance. So this D1 is always going to be greater than D2 in terms of strength. Because when you have them closer, it's stronger. That's what electrostatic forces are. Furthermore, that means that we can have more things in a tight space, and that'll come together with electron density when we move on to charge. So the thing about charge is we know that a greater charge equals a greater force, which also means stronger bond. But the other thing about a greater charge is it also means more valence electrons, specifically more valence electrons that become delocalized. Therefore, we have a greater electron density. And if you have a greater electron density, as we have seen before, uh, our our metallic bond is between the lattice and the delocalized electron. So if we have more of them, then we have more particles interacting with the metallic bond, and therefore you're going to have a greater force. So this is what we mean about the greater electron density. Furthermore, if there's smaller cations, we fit more into a tighter space, and that once again is going to contribute to this greater density. Now, the cations aren't part of the electron density, they're just the density of the metal, but we would have a greater electron density, making a stronger bond, and also that comes from our larger charge. All right. So what we want for a strong bond are two things: small cations and large charge. So we want small cations with a large charge, and that gives us a strong bond. So we can start looking at trends. So we'll look at trends in melting points. So if we start by looking at group 1 metals, and we bring in our periodic table. Oh, doesn't want to add our periodic table. We're going to refer specifically over to these. Now, group 1 metals all have a +1 charge cation. So we know they're all going to have the same bond strength in between their cations based on the charge. However, as we go down, they get larger. So generally what we see is that the lower we go, the weaker the force, or the weaker the bond. And if it has a weaker bond, then that also means it has a lower melting point. So when we're looking at our metals, specifically our metals in the S and P block, so when we look at S and P block metals, the lower down is also a lower melting point because once again, they're going to be larger and therefore they're going to have a weaker force or a weaker bond holding them together. All right. We can also now take a look at period 3. And we'll look at it in this, we'll do dark blue. So in period 3, our charge goes from 1 plus to 2 plus to 3 plus. And so as that charge increases, our bonds get stronger. Metallic bond strength increases. Furthermore, something you'll notice is these larger cations are actually going to be smaller. So our ionic radius is decreasing, which is wild. But if you go back to ionic radius from a million lessons ago, you'll be able to see that they'll all have the electron configuration of neon as a cation, but just different charges, and the larger charges are going to have a smaller radius. So as we go across the period, we have a greater charge, the metallic bond strength increases, and also, therefore, the melting point also increases. So that's the trend. The last thing I'm going to leave you off with is that when we look at metals, the greater the strength, greater strength of bonds also equals a greater hardness. And we can see this with sodium, magnesium, and aluminum. Sodium is so soft, it can be cut with a knife. It cuts like butter almost. Magnesium is a bit harder, but still can be cut when a ribbon, or also shaved off. If you have like a flint and a magnesium rod, you can shave magnesium off. However, aluminum is the hardest of these three, very hard, and can't be cut. So this is a little bit of metallic bond strength and how we can judge it based on the radius of the ion as well as the charge of the cation. So I hope this helps and have a great day.